Polygon collision is one of the fundamental aspects of modern game design because it provides a core mechanism by which we imitate physics. Any game engine will have a built-in physics engine available. However, at some point, a game developer may find themselves asking, how do computers stop polygons from overlapping? The answer, of course, is normal-based object collision detection. The separating axis theorem states that, given two convex polygons, if there are at most one axis which separates the two, then those polygons cannot be overlapping. There are infinite axes to choose from, however, only axes orthogonal to the sides of each polygon are needed. Before continuing, let's consider the key assumptions needed for this algorithm. All polygons must be convex, defined by a list of vectors, stored in some master candidate list, and the environment we're working in must be tick-based. Consider two polygons, A and B. To determine if there is an overlap, we must project the vectors from object A onto the axis of each of its normal-facing vectors by using the dot product between A's vertices and the vertices of A's normal-facing vectors. Then save only its minimum and maximum projection points along that axis. Next, project the vectors of object B onto the axis of A's normal-facing vectors. Check only the minimum and maximum projection between A and B to find overlaps. Repeat the process for the other polygon, projecting both shapes onto the axis of B's normal-facing vectors. If both objects overlap with one another along all axes of both polygon sets of normal-facing vectors, then the objects overlap. In any other case, they do not. If it is the case that an overlap is detected, resolving collision is made very easy. We can find the axis of minimum penetration by subtracting the overlaps from one another, then forming a vector which represents the magnitude of displacement. The angle of this vector is the normal-facing vector with which the axis of minimum penetration belongs to. Lastly, sum that vector to the vectors belonging to the polygon you wish to displace. The main algorithm by which normal-based object collision detection functions is broken down into two sections: broad phase and narrow phase. Selecting an object by its ID, then determining which object's ID to check against is known as the broad phase iteration. When two candidates are selected, we perform the previously described algorithm, known as the narrow phase iteration. I like to label the broad phase's possible list of candidates as the broad phase candidate list. The broad phase candidate list is the main data structure which will hold all of the polygons which can collide with one another. We must iterate through the candidate list and evaluate each polygon against all others. As you can imagine, this could become computationally draining. The purpose of the narrow phase iteration is to check for early exits in order to skip unneeded overlap detections. Given that most objects will not be overlapping along the axes of many of each other's normal-facing vectors, most of the potential overlap detections and collision evaluations will be skipped. Consider the two vectors v and p. The dot product between v and p is equal to the sum of the products of their x and y components. When you sum the product of two vectors' x and y components, you are comparing by how much the two vectors contribute to one another's x and y directions. If the amount one vector contributes to the x direction of another is opposite to the amount they contribute to each other's y directions, then the vectors are orthogonal. We can take the dot product and divide it by the square of the magnitude of the vector being projected onto to get a scalar value by which we scale that vector to get the projection of the other vector onto its axis. Or we can normalize the vector first by dividing its components by its magnitude. In the first case, we remove the area of the square instead of the magnitude because we must account for how much magnitude that vector contributes along both axes, since the dot product uses the x and y components of both vectors. However, if we choose to normalize the vector first, we can skip this step.